Okay, well, thank you everybody for coming back this afternoon. And today I'd just like to talk to you about some of the chemistry that we're doing at the other end of Canal Street, out on the lakefront there at the University of New Orleans. Also part of the Advanced Material Research Institute. So our focus has been on the development of chemistry based on the use of biomass. Now, biomass, has a lot of essentially sources, but from a chemist point of view, we're mostly interested in essentially agricultural and forestry waste. Because, of course, in this case, we have access to some biopolymers that can be readily converted into what we refer to as platform chemicals. Waste from forestry is a biopolymer known as lignin, and this can be converted into vanillin, and vanillin can be converted into these phenol-like compounds as platform chemicals. And cellulose, of course, can be converted into glucose, which can be converted into these carboxylic acid derivatives as platform compounds. Now, we're interested in this from the point of view that once we get to this point, what do we do with these chemicals, in the sense that in these platform bio-refined materials, essentially, they still come out fairly crude. And so what we're interested in doing is taking these compounds from the biorefinery process to essentially laboratory grade chemicals. Okay. And of course, to do this, we want to do it in a green and sustainable process. And so when we think of the targets that we can access here, two come to mind, in the sense that we can access phenol from lignin, and we can access levulinic acid from cellulose. And both of these, upon hydrogenation, give essentially access to two very important classes of value-added compounds. Essentially, hydrogenation of phenol gives us cyclohexanone or cyclohexanol. These are very important precursors in the nylon industry. Basically, we use about 300 million tons of cyclohexanol a year. And of course, levulinic acid can be useful, from our point of view, most useful for the conversion into GVL, gamma valorolactone, which is a building block in a number of synthetic drugs, as well as has been identified as a potential additive to fuels. Okay, so we're interested in developing chemistry that will convert these platform chemicals into these value-added chemicals. Now, the way we want to do this is to use a green and sustainable process, and ideally, this can be done using a heterogeneous catalysis system. Heterogeneous catalysis basically offers the advantage of the metal is not dissolved in the system, so we can essentially just filter off the metal, recover the metal, and essentially, hopefully, recycle it. The problem with heterogeneous catalysis in general is that it has low reactivity, so then you got to heat the reaction mixtures up, which leads to catalyst instability, and then ultimately metal leaching, and it's a never-ending cycle of low turnover in terms of reaction productivity. So our strategy was then essentially to introduce our transition metal on a solid support. This would make it easily recoverable as well, and exploit nanoparticle reactivity. Now, nanoparticle are very small particles, but because they're small, they have a high surface area and are typically more reactive than normal metal particles. And then putting it on a support hopefully would add to stability, and essentially this would also lead to low metal leaching. Now, the solid support that we've been interested in here for the last couple of years is the clay halocite. Halocite is mined out of the ground, comes out naturally. It's mined in Utah. Comes out as this chalk, but if you look at it more closely, it has a fibrous material. And if you look at it really close here, down at the nanometer scale, you can see that these are actually tubes. They come out of the ground naturally as scrolls. And so we identified these as convenient places to introduce our nanoparticles. So our nanoparticles can go in there, essentially be protected from the environment. Our reactants can come in and go out, and essentially we can then recover our material and use it. Okay, well, Our target here was, since we were doing hydrogenation of a carbon-oxygen double bond, we wanted to use iridium. Iridium is really good at doing that kind of chemistry. And so we developed chemistry around iridium. Now, this is part of a bigger project. We also have developed palladium and copper and rhodium catalysts, which is all part of a big patent that we have essentially going through the process right now. But in this case, what we do is basically take the iridium chloride, reduce it into the metal particles in the presence of a capping agent. Now, that capping agent is really important because it coats the nanoparticles and draws it into the tube. Okay, and looking at the picture of the image here of the material, you can see these little black dots. These are our iridium nanoparticles in here. Okay, what's important to note from this slide is we don't have nanoparticles floating around out here. So all the nanoparticles really get inside the tubes and we get good encapsulation. This particular sample, under the conditions we use, gives us about a 15% weight of iridium relative to the bulk material. Okay. Turns out this adds to stability, has a long shelf life without loss of reactivity. Well, we've applied this catalyst to essentially the hydrogenation of phenol. Now, phenol typically is reduced industrially at high temperatures. We're talking above 150 degrees. At high pressure, we're talking hundreds of atmospheres. Okay, we can do this reaction in the lab at 50 degrees with a balloon of hydrogen. Okay, and so this reaction is done in 12 hours, 95% yield in a solvent system of isopropanol and water. Okay, so we've basically achieved all our goals here in the sense that we've reduced the waste stream, no organic solvents. We've reduced the energy component in the sense that we don't have to heat this too much. And essentially, we don't have to use dangerous high pressures of gas, of hydrogen. Okay. We can also do this same reaction with this catalyst just without hydrogen at all, just using isopropanol as our source of hydrogen. And so it takes a little longer, but we still get really good conversion to essentially the cyclohexane. Okay, and so in this case, we now have a system that's operating. We can recover the halosite after each reaction. And we see here in our recycling systems, in the hydrogenation case, we don't lose activity after at least 5 iterations. So we can keep recycling the catalyst and essentially we recover the metal. Also, what's important essentially from a potential use in pharmaceutical for these applications is essentially we only see about 5 ppm of trace iridium in the products. That's just after filtering. That's not doing any other type of purification. And so clearly we can get through this. We can make pure materials very clean. Now we are in the process of developing the levulinic acid chemistry. Here we've done hydrogenation of levulinic acid using our catalyst. We need a little bit more material, a little bit more iridium. We can get this conversion at 70%, 1 atmosphere and 50 degrees. But if we increase the pressure to 3 atmospheres, which is certainly something we can do in an educational or in an academic laboratory, this is very doable, and we can reduce the temperature down to 25 degrees. Okay, so basically, with our iridium halosite, we basically have improved the catalytic activity and access to these compounds, which industrially right now is way out of this range in terms of ease of operation. So just to sum up here, essentially, the improvement here, the innovation is essentially the recyclability of our heterogeneous catalyst. Just basically reduce the cost of using iridium as a metal. Like I said, we have palladium, rhodium, and copper systems as well. So we're basically going to be conserving those metals going forward. We can run these reactions in green solvents. So basically, from an organic chemistry point of view, there's little waste here. Water is ideal. And of course, with regard to our iridium system, we can run these at low temperature and low pressure. The nanocomposite itself has a long shelf life. We've looked at it for sitting on the shelf for about 6 months, and it recovers without any loss of activity. Well, with that, I'm happy to take any questions that anybody might have.